Water can do a lot of things. I mean, it's a liquid of life. It keeps us hydrated, is great for swimming, and it's a pretty nice drink too. But there's one thing that we can't do. Breathe it. As mammals, we need oxygen to survive, breathing it in through our lungs, where it then travels through our circulatory system and around the body. But what if there were a liquid that we could breathe? Well, that's where perfluorocarbons, or PFCs, come in. As organic molecules, PFCs are composed of carbon chains, which are then branched off by fluorine atoms. As a result of fluorine's high electronegativity, which is its tendency to attract a shared pair of electrons to itself, the intermolecular covalent bond between the carbon and fluorine is very strong. Yet, the same electronegativity causes the perfluorocarbon molecules to have a low polarizability, weakening their bonds with other molecules. These weak bonds give perfluorocarbons one of their most unique chemical properties, their ability to dissolve large amounts of gases, such as carbon dioxide, nitrogen monoxide, but most importantly, oxygen. Now, because these PFCs can dissolve oxygen and transfer it into the body, this gives them a boatload of applications that can be used to help advance biology. Perfluorocarbons found their first biological use as artificial blood substitutes in the late 1970s, imitating blood's ability to help transport oxygen and other gases around the body. While these substitutes were produced starting in the early 1980s, not all made it past clinical trials due to flu-like symptoms and an increased risk of stroke. While not being produced as artificial blood substitutes today, perfluorocarbons paved the way for their production and are still being researched now. Yet, in more recent years, perfluorocarbons have found broader applications with the idea of liquid ventilation, which is basically breathing, but with liquid instead of air. This does sound a little outlandish, but let me put it this way. When you normally breathe, you're not necessarily processing everything from the air into your bloodstream. It's mostly the oxygen that's vital. What you need is something that can contain that oxygen and allow it to filter through. For instance, dissolved oxygen in a PFC solution. Now, there's two types of this liquid ventilation. Partial liquid ventilation, where the lungs are filled partially with PFCs and partially with gas, and total liquid ventilation, which completely fills the lungs with the solution. The former has mostly been used in a medical setting, whether to assist breathing in patients with respiratory distress syndrome, or even to deliver drugs to the body by using a mixture of water and PFCs. Total liquid ventilation, on the other hand, has also been used medically by using a complex system to pump liquid in and out of the lungs. However, perfluorocarbon's high density makes it extremely difficult for the lungs to cycle the liquid without outside assistance, making other applications more conceptual. But this hasn't stopped people from thinking of other ways to use total liquid ventilation, like to reduce the risks of a high pressure while deep-sea diving, or even to minimize the stress of G-force during space travel. Now, take a deep breath. You may not be breathing perfluorocarbons now, but who knows, maybe someday you will.